Hi there, and welcome back to our course on the expression evaluation in MonetDB. Okay, so there's actually one final bit I would like to add to this discussion before we draw a line under this chapter 7 and call it a day for expression evaluation in PostgreSQL and MonetDB. And that's the data parallelism I would like to discuss with you. A data parallelism that is actually implemented inside modern CPUs in the form of so-called SIMD instructions, single instruction, multiple data. So we will have single CPU instructions that access multiple vector elements, multiple adjacent vector elements, perform the same operation on them, on these adjacent elements, and then write out adjacent result elements all in one instruction, all in one step. And the premise here is that these operations on the individual elements of the vectors are indeed independent of each other and can thus be performed in a parallel, in the so-called data parallel fashion. I've brought the well-known picture of the vectors with me again. The vectors that are involved in the binary subtraction operation that we have just discussed in the recent videos, the but calc sub operation of MonetDB. We had two input vectors, the left and the right input vectors, and we wanted to compute the subtraction of right from left. Okay. In a data parallel view of things, in the data parallel SIMD instructions of the CPU, such an instruction would read up to 4 in the version of the SIMD instruction that we are looking at here. Actually, there is versions of the SIMD instructions which can even read even more adjacent elements in one go. But let's assume 4 elements can be read in one go. So these instructions would read these 4 adjacent elements, or which are marked with a brace here, in one go, and likewise would read 4 right adjacent elements in one go, perform all the subtraction computation in that particular single instruction, and would write out 4 result elements all within that single instruction. Okay, so in one instruction we would actually write these 4 leading elements here in the result vector. That would be the result of a single subtraction in operation, a data parallel subtraction operation as it is available in modern CPUs. As I told you, all of this relies on support of the so-called single instruction multiple data, or SIMD parallelism, data parallelism inside the modern CPUs. Such modern CPUs have particularly wide registers that can fit 4 of these elements in a vector at one time. And as you can see, as I've noted down here, if we are processing integers of 32-bit width, then such a 4 integer instruction would actually operate on 4 times 32, that is 128 bits in parallel at once. Okay, so we need registers that can fit 128 bits of data at one point, and we need subtraction operations or arithmetic operations in general that can operate on these 128 bits or 4 package of 32 bits at once. All of this, all these wide registers and all these wide instructions are available in modern CPU instruction sets. So on the Intel side of things, this would be the streaming SIMD extension registers that are being used in Intel CPUs, but other CPU vendors have their equivalent instruction set there. So when we look at the generated assembly code in a minute, we will see abbreviations, strange instructions, names like move double quad word, and this is exactly what's happening here. A quad word would have 64-bit. We are even moving a double of that, like 128 bits at once, and perform arithmetic on 128 bits at once. Okay. Of course, this requires care. Of course, if the if the number of elements which we operate on is not divisible by 4 in this particular case, then there would be residual elements that still need to be processed. This is reminiscent of the loop unrolling situation and Dove's device that we've talked about in the video before this. So there might be some residual elements, like these elements I'm highlighting here at the bottom of the vectors, that would need further processing because they're not being processed by the white instruction that we have issued before. So there might be some residual work to be done. And there's also the issue of what's happening if the result and left and right arrays here, these vectors, might overlap in memory. This might sound strange now, but only because we are switching from the regular single element by single element operation mode to the data parallel efficient wide instruction and wide memory access mode. Such optimizations are all well and good, but they may not sacrifice the semantics, the meanings of the programs that we are going to write. I will come back to this in a minute when we take a few seconds to discuss this issue of correctness and overlapping of arrays in memory. But first, let's take a look at the generated assembly code that is emitted by modern C compilers. And for that, I'm switching back to the Godboll view of things here. What you can see on the left is, again, our BAT-calc subroutine, and it's just the routine that we've considered before, the C version of it. On the right-hand side, you currently see the unrolled version of the routine that uses less loop control for more useful work done during the loops. And we've discussed this version of the routine in the last video. I will now allow the compiler to use vectorization. And that is equivalent to allow the compiler to rely on the SIMD functionality, the SIMD wide registers and the SIMD instructions inside the modern CPU. So let's switch to vectorized or data parallel processing here. Okay, and this would be the code as is now being generated. It's a bit more code if you look at the list of instructions here. And actually, as you can see, there's a bit of code here, this light green marked code, that has no direct equivalent on the left-hand side here. This is the equivalent of the loop body, and as you can see, there's indeed these double quad word move and subtraction operations that we have mentioned on the slide already. We indeed find these on the slides, and we will briefly come back to these instructions and the generated instructions on one of the upcoming slides. But there is a prelude here. There's a prelude here. Before we start zeroing out the indices, we have seen that instruction already. Before we really enter the loop, there is a prelude of instruction here. This light green part. And this is actually some logic that tests for the case that the left and right and result arrays may overlap in memory. And if this happens, this code will detect this. Code will detect this and then switch over to a non-SIMD, non-vectorized version of the code. So the compiler takes correctness and the semantics of the C program seriously, of course. It will only perform the data parallel version of the code, this version of the code, if no overlap is being detected. Okay, that's quite interesting. So let's see what all this overlap business is about. Let's go back to the slides here. Okay, so if we allow vectorization in the compiler, for example, in the CLang compiler, then it indeed uses the SIMD registers, this move double quad word register and instructions that we've just mentioned and seen in the Godboll view. All right, but there's indeed extra prelude code that checks for every overlap. And if it detects this overlap, then a non-vectorized, yet unrolled, but non-vectorized version of the code is being invoked. we can promise to the compiler. We can promise to the compiler that the arrays that we will feed into the BATCalc subroutine, that they will never overlap. Actually, there's a special keyword in the C language that's called restrict. So if we restrict ourselves to a sane memory layout in which the left and right arrays and the result arrays do not overlap, then we promise to the compiler that no overlap happens. The array overlap check is gone, and we will always use the SIMD, the data parallel version of the loop. If you lie to the compiler, it will get its revenge. So if you promise to the compiler using the restrict keyword that there is no overlap, but there is indeed overlap, then bad things might happen. So let's take 1 minute to see what might happen actually. I think let's switch over to a piece of paper here. All right, so let's see whether we can sketch that. Here is memory. So this is memory, and this would be increasing addresses in memory. All right, mem. Can you see that? Okay, I think so. Okay, now let's place the left array in memory somewhere. Here's the left array, left. Okay, and it has elements 10, 20, 30, and 40. Okay, so that would be one input to our BATCalc subroutine. Okay, somewhere else in memory there would be the right array. Okay, let's have that. Right. And let's put the elements 1, 2, 3, 4 in there. And at someplace else there would be the result array. Okay, so the result of the element-wise subtraction of right from left would be stored there. So let's have the result array, and let's have some overlap. Some overlap here. So let's see, 1, 2, 3, 4 slots of result space available in our result array. We of course expect these elements to be filled by our BATCalc subroutine. Okay, and then let's do our computation, and let's assume that there is no overlap. Okay. No, there is overlap. There is overlap, and let's now perform the element-wise. I'm sorry. Let's perform the element-wise subtraction. The element-wise subtraction, no SIMD, no data parallelism involved, nothing. Okay, so 10 minus 1, that equals 9, and that would be the first result to place here. All right. 20 minus 2, here's a 2, that would be 18. Okay. 30 minus, we are looking at this particular address here. It has been overwritten due to the overlap. It has been overwritten by the 9. So what we are actually computing would be 30 minus 9. That would be 21. Okay. And then 40 minus this element. We expected a 4 here. It has been overwritten by the 18 in the meantime. It's 22. So that would be the result of an element-wise computation of the regular element-wise non-data parallel subtraction between the left and right arrays, where we placed the results in the result array, but there was some overlap here. This is the overlap. The overlap might be unfortunate here, but this is the semantics of the C program. And even if we perform the same computation in an efficient data parallel fashion, we must conserve this semantics. This is the correct result if overlap between right and result is indeed present. All right. So you see, just performing a data parallel subtraction where we read 4 elements from the left and right array in one go and then perform the subtractions in one go, this would have yielded a different result. So 10 minus 1, 20 minus 2, 30 minus 3, 40 minus 4, this would have been a different result. All right. So the optimization would have violated the original meaning, the original semantics of the C program, and this is of course not acceptable. No optimization by all means, by risking and violating the semantics of the original program. Okay, so this is why there is some extra checking code in the compiled routines that detect whether there is overlapping in place. So then we have to be conservative and work element by element, or whether there is no overlap, then we can perform the data parallel version of the program. Okay. Let's have a look at the generated machine code for the batcalc subroutine. If we indeed enable the loop unrolling and the vectorization, we will find machine code that looks like this. This is just the core loop, the code for the core loop. This is not the prelude that is checking for the overlap of arrays. This is the core instructions that implement the tied loop. And we see the basic structure that we've seen so many times already. This is the jump back to the loop beginning. Of course, we will enter with a zero out loop instruction, array instruction pointer. Okay, that's klar. So let's finally have a look at the native code that has been generated by the compiler for the batcalc subroutine when we enable vectorization and we enable loop unrolling. And there's actually one more thing going on here. I will come to this in a minute. If you look at this routine, it's really the core routine without the prelude that checks for array overlap. If we enter this particular part of the routine, then we are inside the tied loop that assumes that there is no overlap. So we are operating in a data parallel fashion. Of course, we will start out with zeroing the array index. The array index is again stored in the AX register. There will be some loop control at the bottom of the loop here. If we have not reached the end of the arrays, we will jump back to the top of the loop and then enter the next iteration. And as you can see, if we look down here at loop control, that there are indeed really less iterations to be performed because we advanced the loop counter by 16 in each of these iterations. This is an indicator that the code above here, the code above the pointer, above this line, is indeed performing the subtraction of 16 adjacent vector elements in one go. This means we only have to enter loop control 1024 divided by 16, so only 64 times will we enter the loop control here and have to decide whether we return to the top of the loop. This is a good ratio of useful work that is being done above the line and the loop control that is being performed below the line here. As you can see, as already mentioned, and as we've already seen in the Godbolt view, indeed the compiler made use of these double quad word instructions that can move 128 bits at a time, as you can see here on the left hand side in the comment. Okay, the registers that we are using are the XMMI, XM0, XM1, XM2 registers of the Intel SSE instruction set. All of these registers can hold 128 bits at once. And these move instructions, of course, also move 128 bits at once. This is a particular arithmetic instruction, a subtraction operation inside the CPU that can perform subtraction on 128 bits or 4 times 32 bits in one go. All right. As you can see, each such move indeed moves 4 adjacent integers. All right. And since we are performing loop unrolling here, we have another move instruction here that works on the next 4 adjacent integers in one go. So these two instructions indeed load 8 adjacent integers from the left vector. Then we will of course load the integers from the right hand side vector, perform the first batch of subtraction, load the next stuff from the right hand side vector, perform the next subtractions, only to then store the 8 adjacent integers into the resulting vector. So below this particular line, we have already processed 8 integers. All right. Now a different type of optimization comes into play here, the so-called loop pipelining, where another instance of the loop, the next instance of the loop, has actually been unfolded here. All right, so we are not entering loop control, we are actually entering the next iteration of the loop which had just been placed here directly inside the assembly code. And this next iteration will look at the elements at offsets, at the current offset plus 8 until 11 and 12 until 15. So the next 8 integers are being considered here, processed in the same fashion as we've just seen above. And the next 8 subtracted integer results are being placed in the result array. So all in all, this code performs 16 subtractions on 16 adjacent integers in the left and right input vectors, places these into 16 adjacent slots in the resulting result vector. Okay, and that makes less loop control necessary, and we benefit from that. All right. I hope that you found this insight useful and interesting, this insight into the compilation of tight loops and the operation of modern CPUs in their data parallel fashion using SIMD instructions. This is really one of the strong points of the vector-based, of the column-based operation model that MonetDB implements. And it's so much different from the row-by-row expression evaluation, interpreted maybe expression evaluation by PostgreSQL. All right, quite the difference there. But this is what makes this course interesting, I hope. All right, so let's call it a day regarding expression evaluation. Let's draw a line under chapter 7 on to chapter 8 in the next video. I hope I can see you there. Bye-bye.